Let's take a look at an example problem that combines linear and rotational motion, in other words, rolling motion. A bicycle slows down uniformly from an initial velocity of 8.40 meters per second to rest over a distance of 115 meters. Each wheel and tire has an overall diameter of 68.0 centimeters. In this problem, we're asked to determine the angular velocity of the bike wheels at the beginning of our time period, and then the total number of revolutions each wheel rotates before coming to rest. As like before, I will begin by identifying my given information, and specifically, I will identify them with the symbol that I have to make sure that I'm differentiating between linear variables and rotational variables. So I'm given the initial velocity in meters per second. And so I know that this initial velocity in meters per second will be a linear velocity, right? Angular terms will be expressed in radians, not meters. So I know my initial velocity linearly is 8.40 meters per second. I'm also told that the object ends at rest. The bicycle and the bicyclist end at rest. So my final linear velocity is 0. I also know that my angular velocity at the end will be 0. The bike wheel is no longer either rotating or moving linearly through space. I'm told this happens over a distance of 115 meters, and this is a linear distance. So I know that delta x here is 115 meters. I'm also told that the wheel and tire have a diameter of 68 centimeters. I'm going to take that 68 centimeters and just make it 0.68 meters because I already know that I have other units expressed in terms of meters, and that's going to conflict if I don't convert centimeters to meters. I also know that if the diameter is 0.68 meters, I'm probably more interested in the radius. So I'm going to just cut that in half, right? The diameter divided by 2 is equal to the radius. So that will be 0.34 meters, okay? Make sure that if you're given a diameter, you cut it in half for the radius because we're going to need r in our kinematic equations here on the right-hand side, okay? I've been asked here for the angular velocity, so omega, of the bike wheels at the initial instant. So what I'm solving for is omega initial. That's what I don't know. Now, to go about begin solving this problem, I'm going to look at my equations or my relationships between all of these variables. You'll see very quickly that there's no way to get omega initial purely from the 4 kinematic equations for rotational motion alone. I don't have enough information. I don't know anything about alpha, and I don't know anything about my time. So I can't get omega initial from any of those quantities. However, I do have some information about the linear velocity at the beginning and the radius. And so I can use my expression for velocity, v equals r times omega, right here. I know that my initial velocity will be equal to the radius times the initial angular velocity, right? This works for initial or final as long as they're both at the same moment. So if I'm solving for omega initial, I can just divide both sides by r, and that will tell me that the initial angular velocity is nothing more than the initial linear velocity divided by the radius. That would be equal to 8.40 meters per second divided by 0.34 meters. And that would be equal to 24.7 radians per second. I know there was no radian in the units we had before, but you'll see the meters cancel and we'll be missing a unit there. I know that by default, my angular quantities are expressed in terms of radians, and so I've gone ahead and input the radians there to make it clear that I'm defining my angular velocity in terms of radians per second. All right, so for part B now, we're looking for the total number of revolutions each wheel rotates in coming to rest. We saw earlier with the ceiling fan example that the total number of revolutions is captured by delta theta. Delta theta tells me how many total revolutions I am making, just like delta x tells me how much total distance I'm traveling. So really, I'm looking for delta theta. Can I solve for delta theta? Now, looking at my kinematic equations, again, at this point, I don't have enough information to solve for delta theta from kinematics. However, I do once again have a relationship between a linear quantity here, in this case, delta x, and the radius I'm already aware of, so I can relate delta x to delta theta through my bridge equation. That would be delta x is equal to r times delta theta. And so if I'm looking for delta theta, that would just be, again, dividing both sides by r, that would be the linear displacement divided by the radius of that bike wheel. And so delta x here was 115 meters, and the radius of the bike wheel and tire together was 0.34 meters. And so that would give me a total angular displacement of 338.2 radians. And now be careful, the problem was not asking for the total number of radians the wheel rotated through, it was looking for the total number of revolutions. And so what I'll do before reporting my final answer is just convert radians to revolutions. And I know that in every, let's see, radians wants to cancel, so I'll put radians on the bottom here. So for every 2 pi radians of rotation, that's going to be 1 revolution. And so that would give me my final answer. And again, I'm using my full calculator answer here. I'm not using this actual rounded value, I'm just showing this for example purposes. That would be equal to 53.8 revolutions. So the wheels of that bike turn 53.8 times before eventually coming to rest. And so I've essentially answered both of these question parts by using my bridge equations, purely relating the linear quantities I was given to the angular quantities that I was looking for. All right, let's take a look at parts C and D. All right, so for the final 2 parts of this question, we're looking for the angular acceleration of the bike wheel during this time period, and then the time that it took the bike wheel to eventually come to a stop. So the angular acceleration of the bike wheel will be alpha, right? I'm looking for alpha. If I'm looking for alpha, I'll look and see if I can use any of the kinematic equations now that I've solved for delta theta into my initial omega. If you don't remember, I'll bring those values over from the previous slide. I'd like to note that I pulled the value for delta theta in radians. I'm not using that value in revolutions. I used that value to answer the question, but again, we solve problems using radians, so please don't use revolutions when you're solving problems. All right, so the angular acceleration of the bike wheel alpha can be determined by using one of the 4 kinematic equations now that I know my initial omega, my initial angular velocity, my delta theta, and I also know that the final omega, right? My final angular velocity was still 0. Which kinematic equation would you use to solve for alpha here? If you said equation 2, I would agree with you here. We don't have time still, and so that's the only kinematic equation that I have that does not utilize the time. I'm going to go ahead and write this equation out, and then I will rearrange for alpha. All right, now I'm going to subtract the omega initial squared from both sides and then divide by 2 times delta theta. This is just algebra to rearrange for alpha here. And so that will give me alpha is equal to, right, omega final squared minus initial omega squared divided by 2 times delta theta. So please make sure you can rearrange algebraically for alpha here. If I were to plug in then for alpha, that would be equal to negative 0.90 radians per second squared. And again, I'd like to call out the negative here. The bike wheel is slowing down, and so if I defined the bike wheel to have a positive angular velocity at the beginning, then that means in order for it to be slowing down, my angular acceleration has to be negative. In this case, we don't need to worry about clockwise and counterclockwise so much, as long as you ensure that the signs of your acceleration and angular velocity are opposites. So if my angular acceleration is negative 0.9 radians per second squared, I can now use this value, if I'd like, to solve for the last part of this problem, which is the time that it took the bike wheel to stop. I'd like to point out as well that you are free to use the linear kinematic equations here because we know delta x, my initial velocity, and my final velocity. And now that I've got an alpha, I could solve for a, if I wanted to, using my bridge equation. So you have total freedom in how you solve these problems. And now that we have so many different relationships, there are many different ways to solve problems. However, for the sake of this example, I'm going to use another rotational kinematic equation to solve for t, the time it takes the bike to come to a stop. Again, I'll use that first equation because it's the most simplistic and the least number of variables and terms. So that means that my final angular velocity is equal to my initial angular velocity plus my angular acceleration multiplied by my time. I will rearrange this equation for time by subtracting the initial omega from both sides and dividing by alpha. So that would look like this. T is omega final minus omega initial, right? The change in my angular velocity divided by alpha, my angular acceleration. That would be equal to, since omega final is 0, that would just be 0 minus 24.7 radians per second divided by negative 0.90 radians per second squared. Now, again, will give me a positive time. My negatives will cancel, yielding a time of 27.4 seconds for that bike to come to a full and complete stop. All right, so we've just solved the problem relating linear and rotational motion using our rotational kinematic equations and our 3 bridge equations for connecting linear and rotational motion when dealing with rolling motion, like in the case of a bicyclist. Now, this concludes our series of videos on rotational kinematics. Please take a look at Canvas for some additional practice problems to continue to develop your skills.